All right, thank you for the invitation and thank you all for coming. This is joint work with Hill and Hopkins. As you might have heard, I've been writing a book for the last couple of years on what we did with the Curvaire invariant theorem, and I've spent a lot of time trying to think of the best way to explain why we use the model structure on the orthogonal G spectra that we do, and that's what this talk is about. So I'm going to start with some very elementary considerations about model categories. So let's say M is a pointed topological symmetric monoidal model category. You can think of the category of pointed topological spaces if you like. And let's say we have a small category J, and we want to look at functors. We want to look at functors from J to M. And so this is J-shaped diagrams in M. And I want to put a model structure on that. That's called the projective model structure. And here's how I do it. If I've got a functor, X, first, this is some notation. If I have a functor from X, from J to M, I will denote its value on an object, little j, by X sub j, rather than X parentheses j. And I will do the similar thing for maps between functors, also known as natural transformation. If I have such a map if I have a map F from X to Y, I'll denote its jth component by F sub j. Now, such a map is defined to be a fibration or a weak equivalence if each of its components is 1. Then cofibrations are defined in terms of lifting properties. If F is going to be a cofibration, that means each of its components is a cofibration, but that condition is not sufficient. You need a little more than that. Anyway, this is known as the projective model structure on the category of functors from J to M, or the category of J-shaped diagrams in M. Now, this category is tensored over M. What does that mean? That means if I have a functor, X, and an object K in M, which you can think of as a space, we can define a new functor as follows, X smash K, where the kth component of X smash K is the kth component of X smashed with the object K. Similarly, we can do the same thing on maps. A map in M induces a map between functors, X smash K to X smash L in an obvious way. Now, of particular interest is the Yoneda functor. So the Yoneda functor, now notice this, look at the symbol that I'm using for it, that symbol that looks vaguely like a British pound sign. That is a Japanese character, yo, which is the first syllable in Yoneda's name. He wouldn't have used it to write his name, but I'm using it as a symbol for the Yoneda functor.
Can I just say that in like 20 years of doing mathematics, this is the first time I've ever seen someone use a Japanese character in a mathematical as mathematical notation. So congratulations.
Well, it wasn't my idea. It was Eric Peterson suggested this. He told me that this is now the rage in category theory, but I haven't seen it anywhere else. Anyway, we are in symbol deficit, so I figure a new symbol is helpful. Anyway, the value of, so this is the functor L upper J. It's defined for each object in J, and it's a functor from J to M, so I have to tell you what it does on an object K, and it is defined as indicated by this equation. It's the morphism set in J from little j to little k. So the little j is fixed and the k varies here. And if J is an ordinary category, this is a set, and it's a coproduct of points in the model category. And if J is enriched over M, then each of these morphism objects is an object in M rather than a set. So these, I'm mentioning these particular functors because they will be of use later. Now, let's suppose in addition that our model category M is cofibrantly generated. That means it has generating sets I and J. I is the set of generating cofibrations and J is the set of generating trivial cofibrations. Then the functor category is also cofibrantly generated, and its generating sets are defined as follows. They're defined in terms of the Oneda functor, in terms of the Oneda functors. Now I'm going to ask the question that we might ask our calculus students from time to time, which is this. You may wonder, why do we care about model structures on functor categories? And the reason for this, the reason I care about model structures on functor categories is that the category of orthogonal G spectra is such a thing. It is a functor category. If I have a finite group G, the category SP upper G of orthogonal G spectra is an enriched functor category. So I have to tell you what J and M are in this case. So the relevant model category is T upper G. That is the category of pointed G spaces with equivariant maps. And in it, a map between G spaces is defined to be a weak equivalence or a fibration if the same is true of the fixed point map from KH to LH, where H ranges over all the subgroups of G. So a map is a fibration. A map between G spaces is defined to be a weak equivalence or a fibration if the same is true of all of its fixed point maps. Now, this definition is used because of a theorem of Bredon, which says that a map of GCW complexes is an equivariant equivalence if and only if this condition holds. Now, cofibrations are defined in terms of lifting properties, and it's cofibrantly generated. And here is the set. Here are the sets of generating maps. So you take the usual generating maps. So for cofibrations, you want to consider the maps of inclusions of spheres into disks with disjoint base points, and you may want to induce up from a subgroup H to G, as indicated here, and similarly for trivial cofibrations. So this is a cofibrantly generated model category. Now I have to tell you what the indexing category is. This is something called the Mandel-May category, which I'm going to describe. So the objects in this category are finite dimensional orthogonal representations of the group G. Now, I have to tell you what the morphism object is for two such representations. So it's going to be a pointed G space, and this is a slightly long-winded definition. Let's let OVW stand for the space of orthogonal embeddings of V into W. They are not required to be equivariant. Just take I want the collection of orthogonal embeddings of V into W, and this is known as a Stiefel manifold, and it could be empty. If the dimension of V exceeds that of W, this space is empty. And G acts on it by conjugation. The space of maps space of non-equivariant continuous maps between G spaces has an action of G defined in terms of conjugation. And the same goes for orthogonal embeddings. Now, if you have such an embedding, if you have an orthogonal embedding, T, little t, of V into W, it has an orthogonal complement. And the dimension of that orthogonal complement is independent of the choice of embedding. So that means you can use that to define a vector bundle over this embedding space, over this Stiefel manifold. And that vector bundle has a tome space, and that is our morphism object. Our morphism object is the tome space of that vector bundle that's related to, so the vector, the fibers in the vector bundle are orthogonal complements of orthogonal embeddings. And it is also a pointed G space. G acts on it by conjugation. And if you have three morphisms, U, V, and W, there's a composition morphism, as I've indicated here, that is induced by, if you have an orthogonal embedding of U into V and a V into W, you can compose them and get an embedding of U into W, and that leads to this composition morphism that I've indicated here. Now, this map, this composition morphism is equivariant. Remember, all the spaces in sight have G actions, and this map is equivariant, even though the embeddings, the orthogonal embeddings that we're considering don't have to be equivariant. It still turns out that this composition morphism is equivariant. Now, here are some examples of these morphism objects. So the simplest case, let's consider the case where V is the trivial vector space. W can be anything you like. So that means there's just one orthogonal embedding. Just send the trivial vector space to the origin. And that means we're looking at a vector bundle over a point, and the fiber of that vector bundle is W. So the tome space is the one-point compactification of W, denoted by S upper W. Next example is what I mentioned before. If the dimension of V exceeds the dimension of W, then there are no embeddings. The embedding space is empty. And so now we're looking at a tome space of a vector bundle over the empty set, and we still have the pointed infinity. Even if we're looking at a vector bundle over the empty set, the tome space still has a pointed infinity. So JGVW is a point in that case. It is always a pointed G space. In this case, it's a single point. The third example I want to think about, I want to draw to your attention, is when V and W have the same dimension. And in that case, the space of orthogonal embeddings is the orthogonal group. The vector bundle over it is zero dimensional. So its tome space is the base space with a disjoint base point. So it's OV plus, meaning the orthogonal group with a disjoint base point. So those are three examples of morphism objects in this category, and you can work out others. Now, an orthogonal G spectrum is an enriched functor from the category J sub G that I just defined to the category of pointed G spaces, T upper G. So this means it consists of a collection of pointed G spaces, X sub V, one for each representation of G, and structure maps. You always get a structure map as indicated here. In particular, X sub V comes equipped with an action of the orthogonal group O of V. That is part of that's built into this functor category. And we can talk about the Yoneda functor. Remember, the Yoneda functor is defined for every object in the indexing category. In this case, the objects are representations V. So we get something known as the Yoneda spectrum, which I denote by S minus V. So it's defined, its Wth component is the space JG of VW. So this is the Yoneda spectrum. And its structure maps are related to composition morphisms in JG. And in particular, if V is 0, then we're looking at the sphere spectrum. Its Wth component is SW. So this is the sphere spectrum. So I'm denoting the sphere spectrum by S upper minus 0. The advantage of this symbol is that there's no possibility of confusion with the usual 0 sphere, which consists of 2 points. And you don't need a fancy font to write it. Now, so this is the category of the category SPG of orthogonal G spectra is the enriched functor category, as I've just described. So as such, it has a projective model. It has a projective model structure, as I boringly described before. Now, this is not the model structure that we want to use. It needs to be modified in 3 different ways in order to get the one that we really want. So I'm going to tell you what these 3 different ways are, 3 different ways of modifying it. 1, we know from experience as stable homotopy theorists that the notion of weak equivalence that I've defined is too rigid. We don't want to say a map between spectra is a weak equivalence if it induces a weak equivalence in every space in the spectrum. That's too inflexible for us. We want to have stable equivalences. We want our equivalences to be, we want a much looser notion of equivalence, stable equivalences. And those, and I'll say more about this at the end of the talk, but passing from the projective model to the projective model structure where weak equivalences are defined in a very rigid way to stable equivalences is actually a form of Gauss field localization. I'll get to that later. Second condition is we need a model structure that plays nicely with change of groups. And this is what I mean by that. If I have a subgroup H of G, then there is what you could call a change of group adjunction, meaning that there's a restriction functor from G spectra to H spectra. And there's an induction functor going the other way, where if you have an H spectrum, you smash it over H with G plus, and you will get a G spectrum. And these functors are adjoint to each other. The left adjoint is the induction, the right adjoint is the restriction. Now, we want this to be a Quillen adjunction, meaning the left adjoint is supposed to send cofibrations of H spectra to cofibrations of G spectra. Now, as I've defined cofibrations previously, this is not the case. The projective cofibrations do not include projective cofibrations in SPG do not include ones induced up from SPH in this manner. We need to enlarge the class of cofibrations in SPG in order to make this a Quillen adjunction. And I'll say more about that later. Okay, so I've given you 2 ways in which we need to modify the projective model structure in SPG, and there is a third one. It needs to be positivized, and that's a term I will define later. And it turns out that we need to do this if we want to get a reasonable model structure on the category of commutative ring spectra, which is sitting inside the category of all spectra. And it turns out that we have to, in order to make this work, we need to make the class of cofibrations a little smaller than it was before. So I'm going to call this confining the class of cofibrations. I'll get to this later. So after we do this, one thing that happens is the sphere spectrum is no longer cofibrant, which is a little bit weird. Sphere spectrum, after you do this, the sphere spectrum isn't cofibrant. And this is unavoidable for reasons that I will explain later. Okay, now, if you're going to remember one slide from this talk, this is the one you should remember. This shows 8 different model structures. So in the upper left-hand corner, we have the projective model structure that I described earlier. It can be stabilized to give us the stable model structure, and it can be positivized to give us the positive model structure, and so on. You have these three constructions you can do, and they commute with each other. You can do them in any order, so you get a total of 8 different model structures on the category of orthogonal G spectra. And the one we want is the one in the lower right corner, the positive, stable, equifibrant model structure. Yes, they are. I will explain that. You could actually have arrows pointing in both directions for the following reason. We're talking about model structures, different model structures on the same category. And the functors, the relevant functors here are all identity functors. And all these arrows represent the identity functor. Now, the arrow, so you have identity functors. So for any 2 of these model structures, you have identity functors going in both directions. One direction is a left Quillen functor and one isn't. And the arrow indicates the direction in which the identity functor is a left Quillen functor. So yes, the vertical arrows are going in the correct direction. The 4 model structures at the top were described by Mandel and May in their book on equivariant, on orthogonal G spectra. The 4 at the bottom are new. And as I said, our model structure of choice is the positive, stable, equifibrant one on the lower right.
Doug, can you just go back to the slide one quickly, just to make sure I understand the equifibrant adjective? That word is kind of the one that's saying that it's behaving well with respect to the restriction functors.
Yeah, equifibrant means the change of group adjunction is a Quillen adjunction.
Okay, right. Thanks.
That's a new term. You will not have seen that term before unless you've heard me talk on this previously. Anyway, it's a new term. Okay, so I'm going to describe some methods of producing new model structures from old. So the first thing I have to talk about is something called the Trons-Kahn transfer theorem. Trons, I'm not sure I'm pronouncing his name right, was a student of Moerdijk who published the theorem I'm about to say in 1994, and as far as I know, this is the earliest published version of it. But anyway, let's say, before I state the theorem, I need a definition. So we start with a cofibrantly generated model category M, and another category N, which is bicomplete, that is, it's closed under limits and colimits. And let's say we have a pair of adjoint functors relating these categories. Now, let me repeat, M is a model category, N is not. And I'm going to define a model structure on N with the help of these functors in a moment. But I want to put some conditions on, some technical conditions on this. And so there are 2 of them. So M is assumed to be, M as in Mary is assumed to be cofibrantly generated. So it has generating sets, cofibrant generating sets I and J. And so I can apply F to those and get morphism sets in N. And I want those morphism sets to permit the small object argument. So this is a technical condition about model categories. I want to be able to do the small object equivalent small object argument in N with these morphism sets. And the other thing I need is that if I use Fj to build up cell complexes in N, I get maps in N that I want to map to weak equivalences in M. I want you to take relative Fj cell complexes in N to weak equivalences in M. These are two technical conditions that one can ask for of these functors. And if these conditions are met, then I say that the adjunction is a transfer. I'm calling the adjunction a transfer adjunction, and the pair of functors a transfer pair if these two technical conditions are met. Now, the reason I want this is because of this theorem. Let's say we have a model category M and a bicomplete category N and a transfer adjunction between them. Then you can get a model structure on the second category N, known as the transferred model structure, in which Fi and Fj are the generating sets. And weak equivalences and fibrations in N are taken to be maps that are sent by you to weak equivalences and fibrations in M. So if these technical conditions are met, you can transfer the model structure on M for Mary to the one on N for Nancy. And when you do that, the pair of functors is a Quillen pair, meaning that F sends cofibrations in M in Mary to cofibrations in Nancy, and U sends fibrations and trivial fibrations in Nancy to fibrations and trivial fibrations in Mary. And this is our main tool for constructing new model structures. Now, let me point out, N doesn't have a model structure to start with. M is a model category. N for Nancy is a bicomplete category, and we have these two functors with certain conditions, and then we can get a model structure on Nancy from the one on Mary. Okay, now, so now I'm going to suppose that we've got two pointed model categories, M and N, with a pair of adjoint functors between them. And I want to assume that U preserves weak equivalences. U sends weak equivalences in M to weak equivalences in M prime. I am not assuming that this is a Quillen adjunction, meaning I am not assuming that F sends cofibrations in M prime to cofibrations in M. I'm not assuming that. Okay, then I'm going to get a new adjunction out of this. Look at the middle row of the diagram. It's a, I take the product of M and M prime and map it to M as indicated. There's a functor from M cross M prime to M that's indicated in the top row, and there's a functor from M to M. There's a functor going the other way, which is indicated in the bottom row. And these two composites are these are adjoint functors, and I'm going to refer to this as the enlarging adjunction. And it's a transfer adjunction, so it gives me a new model structure on M. It gives me a different model structure on M from the one I started with. I've got a model structure, I'm given a model structure on M cross M prime, and I'm going to use that to produce a new model structure on M, the M on the right. And it will have the same weak equivalences as before, but it will have more cofibrations than we had before, because maps, the image of cofibrations in M prime are now cofibrations in M, where they might not have been before. Okay, so I'm using this adjunction to get a new model structure on M. And the case of interest for us is the following. M is the category of orthogonal G spectra, and M prime is the product over all proper subgroups of H of G of SPH. That's the case of interest for us. And then U is built out of restriction functors, and F is built out of induction functors as before. And so this is going to give me a new model structure on SPG with more cofibrations. I'm calling this equifibrate enlargement. This is going to give us the cofibrations the additional cofibrations we need to make the change of group adjunction a Quillen adjunction. And so this model structure, this enlarged model structure on SPG, plays nicely with the norm functor and with geometric fixed points, which is why we want to do it. We need the norm functor and we need the geometric fixed points, and we need a model structure that plays nicely with it. And this is how we can get it. Now, positivization, what is that? So as in the beginning, let's say we have a pointed topological symmetric monoidal cofibrantly generated model category. That's a lot of adjectives, and a small category J. Now, suppose further that J has a full subcategory K and an inclusion functor alpha. Now, this means we have a precomposition functor from M upper J to M upper K. If I have a functor from J to M, I can precompose it with alpha and get a functor from K to M. Now, this functor is known to have both a left and a right adjoint, and they are the left and right con extensions denoted by alpha shriek and alpha inverse shriek, alpha inverted shriek, as you see there. Anyway, I'm not going to use the right adjoint. I'm only going to use the left adjoint. So I've got an adjunction here as indicated. And it's a transfer adjunction. So I can use it to take the projective model structure on MK and get a model structure on MJ, which is different from the one I started with. And I will say now how it differs from the one I started with. Let me point out something about this left con extension alpha shriek. If I have an object in MK, the resulting object in MJ is defined as follows. Some of the components of it are points. If you have an object little j that isn't in the subcategory, then the value of the functor on that object has to be a point, has to be the terminal object, or a point. Now, the Trons-Con transfer theorem gives us an induced model structure on MJ, which differs from the projective one. And here's how it differs. A map is a weak equivalence or a fibration if Fj is one, but it only has to be one if J is in the subcategory. It doesn't. We don't care what happens if J is not in the subcategory. So that means, so this is a weaker condition. A weaker condition for F to be a equivalence or a weak equivalence or fibration. So that means there are more weak equivalences and fibrations than we had before, and that means there are fewer cofibrations. There are fewer cofibrations, and here's what has to happen with a cofibration. If you've got a map which is, let's see, an induced cofibration, a map F from X to Y is a cofibration only if F sub J is an isomorphism on components that are not in the subcategory J. So it's much more restrictive. If you have a map F from X to Y, it's an induced cofibration only if it gives you an isomorphism on components that are not in the subcategory. So we've got fewer cofibrations, and that means we also have fewer cofibrant objects. And so I'm going to refer to this new model structure on JM, on the functor category, as a confinement of the projective one. Confinement in the sense that it's got fewer cofibrations and more weak equivalences, but fewer cofibrations. So so here's the relevant example. So we're starting with the projective model structure on orthogonal G spectra. And I need a subcategory of the Mandel-May category JG. And so here it is. We're going to say that an orthogonal representation is positive if its invariant subspace is non-trivial. In other words, it has to have a non-trivial vector that is fixed by the group. That's what I mean by a positive representation. I'm requiring it to have a non-trivial invariant vector. For example, if the group is C2 and the representation is the sign representation, the one-dimensional sign representation, the only vector there that is fixed by the group is the 0 vector. So that is not a positive representation. Anyway, a representation is positive if the invariant subspace is non-trivial. So I want to consider the subcategory, the full subcategory of JG in which the objects are positive representations. So the positive model structure on SPG is the one that's induced by this transfer adjunction. So the subcategory of interest here is the subcategory of positive representations. So I'm going to call this construction positivization. Now, why do we want to do it? Why do we want to do it? I'm going to tell you why we want to do it. This category is a closed symmetric monoidal category. It has a nice smash product. So it has commutative ring objects in it that are also known as E-infinity ring spectra. Now, there's a technical problem that I'm going to describe, and there's a technical problem that arises when you want to put a model structure on it. And the issue here has nothing to do with the fact that we're dealing with equivariant spectra. It's not an equivariant issue. So I'm going to assume for simplicity that the group is trivial. This is a problem that exists even if the group is trivial. So we would like to define a transfer adjunction that looks like this. So COM-SP stands for the category of commutative ring spectra. There is a functor to it called the sim functor, which is defined as follows. If you have a spectrum X, you can form a free commutative algebra out of it that's defined as I've indicated here. Sim n is the nth symmetric product functor. So you take a spectrum X, you smash it with itself n times, you let the symmetric group act on it by permuting the factors, and then take the orbit spectrum. And that is the symmetric product functor. I can take an arbitrary spectrum X and look at the wedge of all of its nth symmetric products, and that becomes a commutative ring spectrum in a straightforward way. So that's the way to form the free commutative algebra on a spectrum. And so that gives me a functor from spectra to commutative ring spectra. And then I have a forgetful functor going the other way. And these two functors are adjoint to each other. So Okay, so I could use this to define a model structure. I could start with the projective model structure on spectra and use this to define a model structure on commutative ring spectra, but it's not the stable. We want to be able to start with the stable model structure and do this. And it turns out that there's some problems with that I will describe now. So we need this. One of the things we want to happen is that the nth symmetric product functor has to preserve weak equivalences between cofibrant objects. That's one of the properties it's supposed to have. Now, I have not yet defined the stable model structure, but I'm going to give you a little hint at it. There is a map from S-1 / S1 to S-0, which is a stable weak equivalence. Now, roughly speaking, the spectrum on the left is the spectrum whose 0th component is a point, and its other components are spheres of the appropriate dimension. Its nth component is the n sphere if n is positive, but its 0th component is a point. This map is a stable weak equivalence. Now, I want to apply the functor SP or sim2 to this. Now, sim2 of S-0 is the same thing as S-0, and that's a consequence of the fact that S-0 is the unit for the smash product. But it turns out that the gadget on the left, sim2 of S-1 / S1, is wildly different. It's something completely different. It has a description in terms of the classifying space for the symmetric group on 2 letters. Anyway, it's wildly different. It turns out it's a completely different object. So this map now, the map that I get by applying the second symmetric product functor to this stable equivalence is not a stable equivalence at all. These two guys are wildly different, and this is a problem. This is a technical problem. And it was first noticed by Jeff Smith in the 90s. And it's a problem that makes it tricky to define a model structure on the category of commutative ring spectra. So there is a way around it. Now sim2 is supposed to preserve weak equivalences between cofibrant objects. If both of the objects inside here are cofibrant, it doesn't, so we have a problem. So we're going to positivize the stable model structure on SP as I described before. And when we do that, the sphere spectrum is no longer a cofibrant object, which means we don't need the symmetric functor to convert this map to a stable equivalence, because it's not a map between cofibrant objects anymore. So that means our problem disappears and we get ourselves a transfer junction. So we have to change the model, we have to positivize the model structure in order to be able to build, we have to positivize the model structure on the stable homotopy category in order to be able to build a model structure, a stable model structure on commutative ring spectra. And this was, as I said, this problem was first perceived by Jeff Smith, first noticed by Jeff Smith in the 90s. Now, so I've now talked about 2 of my 3 constructions, equifibrant enlargement and positivization, and I still have some time to talk about stabilization, so I'm going to do that now. Now, stabilization, as I said, is a form of Bousfield localization, and Bousfield localization might be the best construction we have in model category theory. So I'm going to say some general things about it. We start with some model category, and we want to make a new model structure on its underlying category in the following way. We're going to keep the same cofibrations that we had before. We're going to keep this, the collection of cofibrations isn't going to change, but we're going to enlarge, we're going to expand the class of weak equivalences in some way. We're going to say that we're going to allow more maps to be weak equivalences. Now, that means we have more trivial cofibrations than before. A trivial cofibration is a cofibration that is also a weak equivalence. Since we have more weak equivalences, we have more trivial cofibrations. And that means that we have fewer fibrations than before. A fibration is a map that has the right lifting property with respect to any trivial cofibration. If there are more trivial cofibrations, that means this is a more demanding condition and it's satisfied by fewer maps. So we have fewer fibrations than we had before. We keep the cofibrations the same. We enlarge the class of weak equivalences, and that means we're shrinking the class of fibrations. And that means that we're changing the nature of fibrant replacement, and we're making it more interesting. Now, the hard part of doing this is you've got to prove that what you end up with is a model category. And that means you have to prove that it satisfies the factorization axiom for a model category. And in particular, you have to be able to prove that every morphism is a trivial cofibration followed by a fibration. And this usually involves some delicate set theory. Bousfield did the set theory, but most homotopy theorists I know hate set theory, have an aversion to it, and don't want to deal with it. Bousfield is the notable exception, and he figured out how to deal with this. So what he found is that if M has certain properties, you can do this. The model category M has to have certain properties. If it has these properties, it doesn't matter how you want to enlarge the class of weak equivalences. You can enlarge the class. If M is a nice model category, you can enlarge the class of weak equivalences in any way that you like, and you'll get a new model structure. So here are some examples. Let's say T is the category of pointed topological spaces, as it's usually defined. That means weak equivalences are maps that induce isomorphisms of homotopy groups. And all objects are fibrant. Now, let's say we expand the class of weak equivalences by saying we don't need a map to be induce an isomorphism in all homotopy groups, but we only want it to do it up through dimension n. Suppose that's our notion of weak equivalence. Okay, then you can do this, and it turns out that the fibrant replacement functor in this new model structure is the same thing as the nth Posnikov system. In other words, you take a space and you kill all of its higher homotopy groups by attaching cells, blah, blah, blah. And that is the fibrant replacement functor in this new model structure. Okay, that's one example. Now, the example that you might say made headlines in the late 70s is this. Let's let H be your favorite homology theory. Little h star is your favorite homology theory. And we're going to say that the class of weak equivalences is all maps that induce isomorphisms in this homology theory, whatever it is. Then the resulting fibrant replacement functor is Bousfield's famous functor L sub h. That yeah, it's known as Bousfield localization with respect to that homology theory. You can do the same thing in the category of spectra, and in the category of spectra, the functors L sub kn and L sub en are fundamental tools in chromatic homotopy theory. And these are the functors that make chromatic homotopy theory possible. Now, a third example, the example that's relevant to this talk. So let's say we've got the category of spectra with the projective model structure, and I'm going to expand the class of weak equivalences to include all maps that induce isomorphisms in stable homotopy groups. So it's a much weaker condition than saying that a map has to be a weak equivalence at every level. Instead, it's merely required to induce an isomorphism of stable homotopy groups. Then you can do Bousfield localization, and miraculously, the resulting fibrant objects in this world are precisely the omega spectra. And we'll call this stabilization. This observation is originally due to Bousfield and Friedlander. They made this observation in a paper in 1978. Anyway, this is what I mean by stabilization. Now, here's some more comments about it. In general, there are two ways that you can describe Bousfield localization. One is you can say what the new weak equivalences are. You can describe the set of maps that are supposed to be weak equivalences. Now, in order to do this, you don't have to list all of them. You don't have to specify all of the new weak equivalences. You have to specify some of them. And if you invite one to the party, she'll bring all of her friends. So if you specify that certain maps are weak equivalences, that will force a lot of other maps to be weak equivalences. Okay, so that's one way to describe Bousfield localization, is you say, okay, here's a bunch of morphisms in the category that I'm declaring to be weak equivalences, and then go from there. The other thing you can do is you can describe the new fibrate replacement functor. You can do that. Now, it is usually the case that a map is a weak equivalence in the new model structure if and only if the induced map between fibrate replacements is a weak equivalence in the original model structure. For example, a map of spaces or spectra is a Kn equivalence if and only if its Kn localization, the Kn localization of the map is an ordinary weak equivalence. Now, I'm going to end by saying how we do this in the case of interest in the category of orthogonal G spectrum. So I can do both of them. So for each representation V, we define a stabilizing map S sub V that goes from S minus V smash S upper V to the sphere spectrum as follows. Now let me point out that S minus V here is a spectrum defined earlier. S upper V is a space. It's the one-point compactification of V. I'm allowed to smash a spectrum with a space and get another spectrum. And I'm defining a map from that spectrum to the sphere spectrum as follows. I have to tell you what it does on each component. So the Wth component of S minus V smash SV is as indicated here, and the Wth component of the sphere spectrum is as indicated on the right. And we need a map between those two guys And the map we need is actually the composition morphism in the Mandel-May category. That gives us our map. Now, as long as V isn't 0, this map is not a projective equivalence, but we're going to define it to be a stable equivalence. It does induce an isomorphism in stable homotopy groups, even in equivariant stable homotopy groups. So we could say, okay, I'm going to take this collection of maps. I've got one for each representation, and I'm declaring all of them to be weak equivalences, stable equivalences, and then I'm going to use that to define Gauss field localization. So that's one way. The other way is to say what the new fibrant replacement functor is. So here it is. Let's let rho stand for the regular representation of G. Then if I've got a spectrum X, I'm going to define a new spectrum Rx as indicated here. I have to tell you what its V component is for each V, and it's the homotopy colimit that you see on the right. So that concludes my talk. Thank you very much.
Okay, I'm going to unmute everyone so we can thank him. All right. Okay, and I will remute people to cut down on the background noise here. Okay, and are there any questions? Okay, well, if not, then we'll wrap it up here for today. We will meet again in 2 weeks, and Eva Honing from University of Hamburg will give our talk and the title to be announced. Okay, thanks, everyone.